Hello everyone, my name is Tommy Jung. I am from University of Washington in Seattle. Today I'll be talking about Ruche networks. For today's talk, we'll first begin with some motivation for Ruche networks, and we'll talk about the important concept called physical design awareness. And then we'll talk about what Ruche networks are, and we'll see how we can apply Ruche networks to an example Manycore architecture. And finally, we'll present how Ruche networks can be physically implemented. First, we begin with a question: why are NoCs in real chips mostly just simple meshes? Many interesting NoC topologies with non-local links have been proposed in the past. However, in practice, most NoCs taped out in silicon have been simple mesh networks. So what are the key properties of the 2D mesh network that makes it so popular? We argue that physical design awareness is a first-order constraint for NoCs. As we know, placement of gates and routing wires are the major steps in physical design. Most designers use automatic place and route to perform this task. However, the underlying problem is NP-complete optimization problem, so the tool can take a long time to converge on a good solution. From our experience, APR of 6 mm square could take over 36 hours on the fastest Xeon machine. We could imagine the 600 mm square design, which is equivalent to a modern GPU, could easily take over a week. Because of this extremely long time to result, this creates a significant risk to meeting the tape-out deadline. So the key takeaway here is that we need to be very conservative about how our NoCs are wired to ensure that APR runs without any issues. This is one of the reasons why 2D mesh networks have been so common. So how can we structure a design to make physical design easier? First, we can partition the design into many smaller replicated subblocks. Smaller subblocks take a shorter amount of time to run APR, and this allows us to exploit the symmetry and reuse. Many previous NoC designs are asymmetric, and this compounds the physical design effort by having to redesign many different versions of the same tiles. Second, the top level that instantiates the subblocks and wires them together should be very simple. Wiring connections for subblocks should have very similar wire length and similar timing deadlines. And the majority of design complexity should be pushed inside subblocks as much as possible to take advantage of reuse. 2D mesh topology is popular because it fulfills these properties by providing simple, regular, local connections between subblocks. This regular structure reduces the APR runtime and reduces the physical design risk. If 2D mesh networks are so great, then why are we motivated to find different topologies? First, packets are limited to 1 hop per cycle, even though the raw speed of wires can be much faster. And as the number of nodes increases, the network diameter becomes substantial, and the bisection bandwidth becomes a bottleneck. Also, because the router area grows with link width, the routing resources are underutilized, both between tiles and inside a tile. So what are the problems that we're trying to solve with Ruche networks? First, we want to have a Wire-Maximal NoC that considers physical design as a first-class constraint. We want to convert excess wiring into network performance, and we want to efficiently utilize excess wires without too much hardware overhead. And we want to propagate packets at the full speed of wire. And finally, we want low hardware complexity and have critical path and routability under control. Here we are showing a row of tiles connected by bidirectional links as an example of a basic mesh network. I am only showing a single row for simplicity, but we can imagine there could be multiple rows and links going north and south as well. Since these links are only connecting to the nearest neighbor tiles, we'll call them local links. Now we add the additional links that jump multiple hops. These are called Ruche links. These links consume the routing resources of the skip tiles without adding any logic inside those tiles. The term Ruche vector means the number of hops that these links extend. We changed the routing algorithm so that if a packet needs to travel greater distance than the Ruche vector, then it will take the Ruche link. Otherwise, for the local traffic, it will still utilize the local link. After replicating Ruche links on every tile, now we have a complete Ruche network. Because of the Ruche vector of 3, the network diameter decreases from 8 to 4, and the bisection bandwidth increases from 1x to 4x. Each tile in the Ruche network has 100% identical logic and wiring, so the tiles can be replicated and placed directly abutting each other. This addresses the physical design challenge mentioned earlier. Here we show a more complete picture. On the left side, we have a half Ruche network where the Ruche vector 3 is only applied in horizontal direction. On the right side, we have a full Ruche network where we added the Ruche vector of 2 in vertical direction. Designers can vary the Ruche vectors depending on how much access routing resources are available in each direction. Now we'll talk about the router architecture. As mentioned earlier, one of our main goals is to have low hardware complexity. We want to efficiently utilize excess wires without adding too much hardware overhead. Here we are showing crossbar inputs for the 2D mesh router with dimension order x and y. The router has 5 ports, P as processor and north, south, west, east. We can see that north and south have 4 inputs, and P has inputs from all directions, and west and east have 2 inputs. Now we add the Ruche direction RW and RE to the router. This is an example of a half Ruche network in X direction. The red in the diagram shows what is being added to the existing router. We restrict some directions that packets can travel to limit the increase in the crossbar area. Therefore, we call this a depopulated router. The basic idea is that packets can get on a Ruche link only from the P port. And once they are on the Ruche link, they can continue on the Ruche link as long as they need to. We're not allowing any direct path from RE or RW to P, because the P is already overloaded with 5 inputs. Also, we're not allowing packets to turn direction from RE or RW to north or south. Instead, if a packet wants to change dimension or get to the destination P, the packet must get off the Ruche link using west or east exits. It turns out that depopulated routers have another benefit besides having low area. Here we are showing a graph of link utilization to complete all-to-all unidirectional communication. There are 16 tiles in this 1D network. All packets are going to east direction. X-axis is the X position of the tile, and the Y-axis is the number of flits sent from this tile. There are 2 bars for each tile. The black bar means the number of flits sent using a Ruche link, whereas the white bar means the flits sent using a local link. The key takeaway is that as the Ruche vector increases, the pressure on the local link increases, because there are less number of endpoints that can be reached by Ruche links. And the depopulated router balances the traffic better, because all the packet needs to get off the Ruche link to get to the destination P. Now we'll talk about physically implementing Ruche networks. Before we begin, we need to think about one of the crucial design challenges that are unique to Ruche networks. With the addition of a Ruche network, there are long parallel wires placed with much greater density. Because of the capacitive coupling, there will be crosstalk-induced noise and delay, and they need to be kept below a certain level to prevent glitch and setup time violation. Fortunately, crosstalk analysis is a standard procedure in modern CAD flow. With parasitic extraction and static timing analysis, we can accurately measure the impact of the crosstalk. However, what we're trying to do in this paper is to provide some guidelines for implementing a Ruche network in a more systematic way. This method involves first understanding the properties of the wires and how the signals behave under different routing configurations. First, we consider different wire spacing to control coupling capacitance. We found that the single spacing is too noisy and too slow for the length of the wires we're considering. Double spacing was ideal for both noise level and routing density. It turns out that any greater spacing is meaningless because the DRC metal density rule will require the gaps to be filled anyway. Also, we can alternate wires on different metal layers to achieve greater routing density without much degradation. In the cross-sectional view, we can see how much space there is between two horizontal metal layers. Because wires are usually thicker than they are wide, and there are two via layers and a vertical metal layer in between. So the coupling capacitance from a different metal layer contributes very little to the total. Second, we want to minimize the Miller effect. When two adjacent wires are switching in opposite directions, the effective coupling capacitance doubles. In order to prevent adjacent wires switching at the same time, we interleave the wires in different stages of Ruche links so that signal arrival time is further apart. Third, we try different inverter stages and drive strength. In terms of a wire length, unbuffered wire delay grows quadratically, and buffered wire delay more or less linear. An inverter with greater drive strength tends to be more resilient to crosstalk, but it also dissipates more energy and is noisier on neighbors. Finally, based on available routing tracks and timing constraints, we adjust the Ruche vector to convert excess wires into network performance. Here we have done some basic analysis shown in this graph. We vary the Ruche vector and measure the sum of total zero-load latencies required to complete all-to-all unidirectional communication. This pattern is quite representative for the traffic between Manycore tiles and memory system. On the x-axis, we have the Ruche vector. On the y-axis, we have the sum of all latencies for all packets. A Ruche vector of 1 does not reduce network diameter. We have the most benefit going from 1 to 2, and there is diminishing return as the Ruche vector increases. However, once it reaches a certain point, the sum of latencies starts to increase again, because there are more endpoints the packets have to travel via local links. This suggests that even a modest amount of Ruche vector is quite sufficient for a significant improvement in network performance. Now we'll apply a Ruche network on an example Manycore architecture. HammerBlade, which is our research Manycore architecture, has two physically separate mesh networks. A remote load or store instruction turns into a request packet, and a response packet comes back asynchronously. The request network is simply x then y dimension ordered, whereas the response network is y then x. Packets are single flip, single cycle per hop, and the arbitration logic is round robin. We envision that in a larger die design, we'll have a multiple instantiation of a macro unit called pod. Each pod consists of 32 by 16 compute tiles, and the top and bottom rows are memory tiles, which provide cached access to the off-chip memory system. The aspect ratio is chosen to be 2 to 1 to provide higher memory bandwidth. We calculated that given the geometry of a compute tile, we have enough routing resources to fit a half Ruche network in x direction with a Ruche vector of 3. This increases the bisection bandwidth from 16 to 64 requests per cycle, and it matches the total cache bandwidth. It reduces the network diameter from 46 to 26, and it brings up the track utilization to 96%. In order to demonstrate that our Ruche network can achieve excellent signal integrity and time enclosure, we placed and routed a proof of concept model in standard cell design. We used GlobalFoundries 12 nanometer as a point of reference. We tried to model the wire length as closely as possible to the actual Manycore design. We interleave the 3 stages of a Ruche link and a local link as a single bundle, and we replicated this pattern for 138 times. In the diagram, we label the wire segments of Ruche link from X0 to X3. We place X1 and X3 on the same metal layer because their signal arrival time is furthest apart, so it's the best way to minimize the Miller effect. We measure the noise select on each wire and group them by the bus type. Here we show the graphs for the two longest wire segments X1 and X2. X-axis is the wire index and Y-axis is the noise select in voltage. The noise margin itself is roughly around 0.2 volt. We can see that the noise select does not go below 50% of the noise margin. There are periodic spikes in the graph, and those correspond to the wires that are next to the power vias that has only one aggressor. From this graph, we can be assured that the noise select is good for the wires that are longest and most susceptible to crosstalk. Next, we measure the wire delay. The graphs are similar to the previous ones. Y-axis is the wire delay, and the gray part of each bar corresponds to crosstalk-induced delay, whereas the black part is the intrinsic wire delay. We can see that the crosstalk delay can be greater than the wire delay. The wire delays are around 30 picoseconds on average to cross 141 micron. And overall, this is enough to meet our 2 GHz timing constraints with some extra slack. So that is the end of the talk, and to summarize, we argue that the physical design has to be the #1 constraint for NoCs. And Ruche Networks is a new kind of NoCs that fulfills this requirement. And Ruche Networks can efficiently utilize excess routing resources to provide greater bandwidth and reduce network diameter. And finally, we analyze using a standard cell design to show that Ruche networks can achieve excellent signal integrity with extreme wiring densities. Thank you.